start with the large language model. So we ended up working on the transformer-based language models, right? And then we are now able to design a language model, and then we can do it very complicated, meaning that we can have a very high number of transformer layers. And then this guy is going to take the input tokens, and then it's going to complete the sentence, right? So it's going to get incomplete sentence, and then it's going to compute the probability of every single next token. And then it's going to sample from that distribution, complete the sentence, give it back to the input, and keeps on doing it till it's over with the completion of the sentence, right? So we can do it with this architecture. We eventually did not use these two parts. We only used the decoder part because at this point we were just designing a language model, so we want to complete a sentence, right? So that's what we have done. And I told you last time that if you just scale everything super large, then you're going to end up with like the noun language models, like GPT, right? Now, large language models is a kind of not a real scientific term. It's just a technical term or industrial term. And the word large is coming before language model because they are really large. So it means they are very deep in number of layers. Every layer is hugely wide. And also they have been trained on a super large data. And this is why we call them large language models. So they are nothing, I mean, in their basic form, they are nothing but basic language models which have been super large. And just to give you an idea how much large they are, well, I mean, you can guess that every single second they are getting larger, right? So right now, probably there are people working on making it larger, deeper, and trained on more data. So that is happening every day. But to just give you a tiny bit of idea how much large they are in practice nowadays, I mean, GPT is the best example because GPT is the one which just made this whole LLM getting out in the market. And GPT-1, which was in 2018, and it was somehow showcasing that this is working, was essentially trained with 117 million parameters. So that might sound large, but it's still nothing as compared to what we have right now. So this was somehow trained with the same architecture we had last session, but the number of transformer layers that repeated there was 12. So 12 of those multi-head plus feed-forward layers, 12 of them, right? And within every single of them, there was multi-head attention, of course. But then GPT-2 came out, and then it had different versions, but the deepest version had 48 layers. So they just jumped from 12 to 48, and the number of parameters was by a roughly factor of 10 or so larger, so it's now 1.5 billion parameters, right? So much larger. But again, this is not a huge growth as compared to GPT-3, which was the thing starting to work and everybody used, right? And it had 175 billion parameters, and the number of layers just increased to 96. And you do know that from GPT-1 to 2 to 3, it was not like ages passing, right? It was a short time as compared to many developments in the scope of artificial intelligence before. So this was a huge growth, like an exponential growth in the size. GPT-4, we really don't know it because there is one point here happening, and that is that the larger the models get and the more powerful they get, the less transparency we get from the industry. And there are a bunch of reasons behind it. I mean, some part of it you can understand. They have the concerns about intellectual property there, because to make those very large models to work, you need to do lots of technical details, some hands-on tricks to make them work. And because of that, people are not happy to just simply share it with everybody. This is one reason. Of course, that makes total sense. But this is not the only reason. There are other concerns as well, because these models are getting crazy powerful, right? And then if you just release everything in the hands of everybody, then it means that you are just giving them the chance to just easily get into the power, which might be harmful to others, right? So this is why people are getting less and less transparent in that respect, because there are some safety concerns there happening. So just to show you how transparent everything was at the beginning, GPT-1 had the model there, the data was available. I mean, we did know what was the corpus that it got trained on. The code was released. GPT-2 was the same. Code was not initially out there, but then later they released it. But at GPT-3, we had the idea about the model, so we do know what is the architecture, how many layers, things like that. But the exact code we don't have access to. And the data, well, we have a rough idea what kind of data was there. But how exactly that was collected, where is the data set, again, we don't have access to that one. But for GPT-4, nothing is out there, right? So we don't know really. We can't just guess like, OK, probably the model dimension got expanded to this, and data is probably that, and so on. Yeah? So yeah, this is what I mean by large model. 175 billion is a crazy number, and we didn't think about it before, right? So I mean, definitely when we were thinking of recurrent neural networks, nobody was thinking of that dimension. Yeah, but transformers enabled us to do that. And the next thing is about the data. So how large is the data is, again, crazy large as compared to many things we had before. So again, a bit of context here. First of all, you might wonder where we get the data. Well, we get the data through different resources. The first one is online resources, right? So this term web text is probably something you hear when you read those papers. Web text, it simply means that you get into like initially web text was somehow developed by OpenAI itself, so a version of it, which means that they're going to go on relevant public articles on internet, but resources which are reliable, things like Reddit and Quora, and then they try to just make a data set out of that. But Wikipedia articles are, again, a good resource for say, web-based text that we can use for training a language model. Coding corpora, you usually go on and make lots of coding texts, meaning that, I mean, Python codes and MATLAB codes and, I don't know, C codes, everything that you can get access to. Again, there are a bunch of resources. GitHub is the best one, of course, and lots of forums where you can ask your coding questions, and they are also resources where they collect data from. And literally, they go look at these servers, and they try to download everything and then try to filter it. Yeah? It's a very tiring job to do, but, well, if you think about the purpose, then it's less tiring. And if you get paid well, you are less concerned. So yeah, this is another resource. Book corpora, it was one of the initial ones, like you go look at lots of books. I mean, there are very good resources. Coherent text, very few mistakes happening there, so it's going to just train your model quite well. And of course, Common Crawl is nowadays the thing, right? Common Crawl is a web service where you can access to the, the whole or a good chunk of internet as a data set, right? But this is a raw data, like the HTML code, right? And then you need to get this one, filter it, clean it. And there is even more important thing is that you need to just care about safety and ethical issues, right? Because when you just get the whole chunk of internet, there are, of course, useful stuff there, but there are also garbage there, and there are also some concerning stuff there which you don't want to be inside your data set, right? So these are things that people do in order to train a language model, and this is a very hard thing to do. And how large it gets, well, when we talked about GPT-1, they only looked into the book corpus data set. Have you ever heard of this data set, book corpus? Anyone knows that? So actually it was done at UofT, you know that. But you can read about it. I put you some articles. You can read about it because there are some changes happened there due to violation of other consent. So they had to change it to book corpus, open book corpus now, so it's not available anymore. But at that point of time, it was available and was about 1 billion words in that data set. So roughly, if you would say, OK, each word is 1 point something token, then you can say it's the same order of tokens, right, inside the whole corpus. And then the model was trained on that, exactly the same thing we did in the last couple of sessions. This is the first thing. Then they went for GPT-2. So at that point, OpenAI just created this web text I told you, and then they used that one to train the models. It was larger, so I could not find exactly how many tokens was there, so I just wrote the size on the memory, so 40 gigabyte, but it still is something that it's not like a big thing for us, but GPT-3 was essentially trained on such a data set, so it was now crazy large. So roughly about 500 billion tokens. And as you can see, any kind of data is there. So they started to just diversify all the data because they wanted the model to be able to talk about everything, right? It can code, it can talk about text completion, it can answer questions, things like that, right? And it's a bit, I mean, I got this one from the original paper of GPT-3. And as you can see here, there was a bit of engineering here in the preparation of data as well. It's not only cleaning the data, put it in the corpus, and then you go over it over and over to train. That was not simply this. They actually came up with a kind of sampling weights as well. So, for instance, when they want to make the batch, you remember when we want to make a batch, what do? We just randomly sample a part of our corpus, right? And they started to give weight to each of these sub-corpuses, right? So essentially, 60% was the weight allocated to Common Crawl, but for instance, this web text was 22%. And you might say, okay, 60% is high, so it means it was only trained on Common Crawl, but you should pay attention that you had so much Common Crawls here, right? Whereas 22% was given to a much smaller corpus here, right? And this means that when they train the whole model, then the whole data in each of these parts of the data set was involving or was involved within the whole process differently. So I put you a bunch of numbers here. For instance, I called it effective epochs, and this means that the whole GPT-3 was trained for 300 billion tokens. It means that you start with a sample and then go for another sample and so on, and the number of tokens finally you have processed is 300 billion. And in that 300 billion training, the Wikipedia articles were gone through 3.4 times. Okay, so this is the effective number of epochs we have done on that part of the data. But the Common Crawl has not been gone completely, right? So we had half of the data involved. And you remember when we started, I told you just think about the definition of an epoch now when you are sampling randomly from a corpus, right? And you see this is not really the whole, I mean, part of data is not even showing up in training exactly, right? But it's okay. I mean, you just have so much data that you don't care about those tiny things. Okay, so GPT-4, again, we don't know really how much data they could collect, and we just have heard that we have done, I mean, some general comments on what kind of data was involved there. Okay, so that's about this size of the data and model in GPT as an example of the large language models that we have nowadays. And for those of you who are interested to know whether we have a data set which is available ready, like for example for simple classification we had CFAR and MNIST and things like that. Do we have anything for language models? I mean, there are a bunch of projects out there, so every couple of years some papers come out and they explain about a project they have done. Some of them are public, some of them are partially public, some parts are not public. Some of them are totally private, like what GPT-4 has used. And the most famous public one is the PILE. So the PILE is a data set collecting quite a fair amount of data, and it's quite large. I would say, I guess it's like the largest public data set for training of a large language model. And if you're interested, you can check their webpage and the paper to see how they have collected those data. And nowadays, many people, when they do research on language models, they use this one as a kind of benchmark to just do the training and other things. But you can understand that this is really exhausting because it's a huge data. You really need to have huge computation power. Now, before I just end up this tiny story part, I just want to give you a few marks here. and that is that, I mean, collecting data is really crucial here. So it's not as before as you think like, okay, I want to just train a classifier. Okay, I go ahead and just collect as much as images as I want, and I label them. I mean, first of all, finding right data is quite hard, and there are lots of ethical concerns about that. So things like, for example, privacy. I mean, do we guarantee that no private data is going to be leaked into our data set? Because the point is that your model is going to learn about that data as well, right? And your model might be able to talk about one individual if there are so much information about that individual inside the data. And are you sure that that data is not private? That person has consent to share the information, right? Other things are like ethical issues. So if you have a data which contains some non-ethical components in it, well, your model is going to learn all of those stuff as well, right? And it's going to just give recommendations, advice on that respects as well, and you don't really want that, right? So there are ethical challenges going on here. Safety issues is again the same thing. Copyright violation. I put you one particular article about this book corpus, and then you can read it through to find out about the fairness of the data set and also the violation of the some acts about the consent of the authors, even though the books were all free books, but there were some legal issues there as well. So you can take a look at that one as well, and also the rights of intellectual properties. This is one other important thing. So if you give so many books of one author to a language model, it's going to start not only to complete sentences, but you're going to start to learn what is the writing style of that author, right? And then the writing style of that author is something coming totally out of that author's intellectual capabilities, right? And you are just copying it into your language model. And then the question is whether this is with their kind of aware consent or not, okay? So this is also an important thing because as an engineer, probably we are always happy to do more and more, right? But the question is whether we are doing it in a right way or not. And believe it or not, for every single of these stuff here, there is an example. So if you go online and just, if you're interested to find out more about that, just go online and check, and you're going to find lots of cases where these one or a couple of them are being violated. So one thing, the reason that I put it here is not simply that I warn you that be careful, don't get in trap or things like that. I mean, this is one part of it, of course. You don't want to get into trouble. But one other part of it is, as an engineer or as a professional, if you get into a position where you are being responsible for doing any of the data collection stuff, you need to give the other side, the one who is sharing the data, this understanding that what's going to happen when they share their data, right? So, I mean, in this intellectual property thing, the example of books I told you, the author probably doesn't understand what's going to happen with the large language model. The one who understands is you, right? And it might be okay if I tell the author, okay, well, we're just training a language model. Give us all of your books and we're going to pay you. And then the guy gets super happy, gives me all the books. But I do know that ethically I'm not doing a very aware way of data collection, right? So the other side doesn't understand what is happening to its own intellectual property. So as someone who is informed, at the same time, is always the thing with any information, right? When you get informed, at the same time, you get ethically obligated to inform the others, right? So this is very important that you put all of these things into consideration. And you might laugh right now, okay, I'm not going to work for OpenAI at some point, but who knows, right? Maybe you get into a position where you can do such a decision, and then it's very important that you share your honest information with everybody so that they're going to get chance to have a kind of aware decision making, okay? So I know this is not really technical about this course, but this is important to emphasize because, as I said, any information, any power comes at the same time with obligation. So that being said, so let's just get out of all of those story a bit and get a bit more into technical stuff. So one thing, if you have a language model, and in particular we're talking about large language models because they are nowadays the thing, if you want to evaluate how it performs, there is one particular parameter or evaluation metric which we call it perplexity. And what is perplexity? It's basically, I mean, the definition is this one, but I'm going to break it down for you. You're going to see that you essentially know what that is. So say I have one sequence, x1 to xt. This is one incomplete sequence. And I'm going to complete it, and say when I did the completion, then it just got completed with L extra tokens, right? So I'm going to get xt plus 1 to xt plus L. These are the new tokens, okay? So I have L tokens coming out, and then your language model is essentially capable of computing the probability of these L tokens, right? Essentially, this is how the language model is generating them. So it's going to compute the probability of every single of them, and then it samples from that, right? Now, this is the probability that is computed by your language model. So you're going to put the probability, take it to power -1 over the length of the sequence. Now, the definition is clear, right? But to just break it down for you, what is happening there, or what we are exactly computing, let's just break it down first. So first of all, this -1 that you see here in the exponent, I can just write everything in bracket 1 over that, right? So this is p to power -1. I write it 1 over p, right? And then the exponent 1 over L, it simply means Lth root, right? So this is what we are computing, right? Now, one thing. If I want to compute this probability, I am computing just probability of xt plus 1 and xt plus 2. Let's just keep everything simple. So L equals by 2, x1 to t. Okay? If I want to write this guy down, how can I open it up? Can I open it up in terms of individual probabilities? So I'm going to write down the first term. You tell me what is the next term. Okay? So the first term is going to be p of xt plus 1 given x1 to t. What's going to be the next guy? xt plus 2 given what? 1 to t plus 1, right? So it's going to be x1 to t and xt plus 1. And I'm going to write everything here x1 to t plus 1, right? Everybody's clear? Now if I have the third token here, it's going to be xt plus 3 given x1 to t plus 2, right? So I can open up this probability here in this form, right? Everybody agrees? So it's going to be the probability of the next token given the whole incomplete sequence. Then the second next token, the whole incomplete sequence, and my first token, right? Everything till the last token, right? So this is simply the chain rule. Everybody's clear? So this perplexity term that I have written here is essentially this guy, right? Yeah? And now, one thing that you can see here is that this guy, every single of them, is the likelihood of every single token we are generating, right? So the first token when I generate, I'm going to compute the likelihood of this token, given everything I had before, right? The second token is going to be the likelihood of the second token, given everything up to the time t plus 1, and so on, right? So perplexity is essentially reversely proportional to the likelihood, right? Now, what do you like to do with your model? Do you want to take likelihood up or down? Up, right? You want to have high likelihood. So what's going to happen to a good model in terms of perplexity? It's going to be low, right? So essentially, perplexity is a reverse form of your likelihood, okay? But people usually write it down in this form because it's a kind of average version of that likelihood. And to see this again, let's just compute the log perplexity. And log perplexity is usually the thing that is reported in the industrial or scientific papers. So logarithm of this perplexity we have computed there. So if I want to compute the logarithm, just look at this one. Or even look at the first term. If I compute the logarithm of that term, what's going to happen to the exponent? It's going to come out of the logarithm, right? So this is going to be -1 over L logarithm of that probability, right? We open the probability using chain rule. What's going to happen to logarithm? It's going to be summation, right? So it's going to be written in this form, right? what is that log of p there? That is the log likelihood, right? When we were training our model, what we were doing? We were maximizing that log likelihood, right? So essentially, your perplexity is nothing but minus log likelihood, right? Exactly the same term that you were trying to maximize. Or minus that thing, exactly the same term that you try to minimize. And that power 1 over L there is somehow averaging everything over time, right? So it's like you're saying, what is the likelihood of the first token I generated? What is the likelihood of the second token till the last token? And what is their whole likelihood in average? That is what is log perplexity. Everybody's clear? So it's not hard for you to see that this is essentially just time average of log likelihoods, which makes sense. And the other property is that, first of all, log perplexity is always non-negative, right? Because that likelihood term, that p here, is something between 0 and 1. It's a probability, right? So logarithm of that term is always negative, minus that guy is always positive, right? So this guy is going to always be positive or 0, right? And the other thing is that when this log perplexity is smaller, or perplexity in general is smaller, likelihood is going up, and this means that your language model is more reliable. It means that every single token is generating, it's more certain about generating it. What is the lowest value you can imagine for log perplexity? 0. And when does that happen? When is this guy 0? Perplexity, no, this log is 0 when, what in terms of likelihood? 1. Likelihood is 1. It means that every single token you are generating, you have no doubt about what you should generate, right? You are 100% sure that the next token is going to be this, next token is going to be that, and so on, right? So lower perplexity means lower confusion, and this is a better thing for your language model. Of course, you don't get to 0 because language itself has a bit of confusion, right? So when I say a couple of words, you cannot say for sure what is the next word always, right? So I can use different words. And there is a bit of perplexity happening in the language itself, so it's not going to be really 0. But the lower it gets, it means that the language model has less confusion, and this means that the language model is somehow more reliable, right?